Dames en heren, ladies and gentlemen, geachte collega's, dear colleagues. I hereby formally open this session and I welcome you all to the public defense of Thomas Konings. Thomas Konings has presented to the faculty the PhD thesis on the topic Atmospheric Chemistry of Gaseous Exoplanets, Data-Driven Modeling and Statistical Inference, impartial fulfillment of the requirements for obtaining the degree of PhD in Science, Astronomy and Astrophysics. Thomas Konings shall now publicly defend the PhD thesis. Thomas Konings, you are invited to give a presentation of about 45 minutes about your work. Afterwards, the examination committee will ask questions and discuss your work with you. I give the floor to Thomas Konings.
Okay, this works, it seems to work. So first of all, thank you all for being here. It's really nice that so many people take an interest in my thesis. And I have a somewhat challenging task today to try to condense 4 years of research into 40 minutes. And what's even more challenging is that it's for a very diverse audience. And typically the first thing you do when you give a presentation is you figure out who you're talking to, which is impossible because there's people that are experts in the field and people that are very much non-experts in the field, which is totally fine, but I'll try my best to make sure that everyone sort of gets something out of this presentation. So my thesis is titled Atmospheric Chemistry of Gaseous Exoplanets, Data-Driven Modeling and Statistical Inference. And in the first half of the talk, I'll really spend some time on properly introducing a lot of concepts within the context of my thesis to make sure that everybody sort of understands why I did the things that I did and hopefully agree that they're not completely useless. So an obvious point to start. What is an exoplanet? An exoplanet is a planet that orbits a star other than the sun. At least that is the definition that I'm going with today for this thesis. And in the bottom part of my slide, hopefully you recognize this, all of you recognize this. This is a schematic of the solar system, or at least the 8 planets of the solar system. So you'll find the 4 rocky or Earth-like planets closest to the sun, and then the 4 gaseous planets, from where Jupiter is by far the largest. And so for a very long time, up until the early 90s, this was sort of all the planets we knew. And that is until 1995, when we discovered the first exoplanet around a solar-type star. A solar-type star just means that it's a star similar to our sun, typically in mass. And it was already quite interesting because the first exoplanet we discover, it's titled 51 Pegasi b, is twice the size, or about twice the size, of Jupiter. So the very first exoplanet is already twice as large as the largest exoplanet in our own, or the largest planet, rather, in our own solar system. And that's not the only interesting part. If you were to take 51 Pegasi b away from its own star and place it in our own solar system, it would be orbiting in between the sun and Mercury. So the very first exoplanet is huge, and also it's orbiting 8 times closer to its host star than than Mercury is orbiting our own sun. And so from the very beginning of this field of exoplanets, scientists were confronted with the possibility that our solar system might not be representative for these exoplanets out there. And they were right, because 30 years later, we have around 6,000 confirmed exoplanets. Actually, last time I checked, we were 11 short of reaching 6,000. And if there's one thing we can conclude, is that these planets are diverse. They span a wide range in masses, radii, temperatures. And I'm showing you this figure on the right, which shows the orbital period on the horizontal axis. For Earth, this would be 365 days. And on the y-axis, the mass, measured in times the mass of Jupiter. And if we now overplot this figure with the planets of the solar system, we get this. And so this confirms indeed that at least for the distribution or population of exoplanets that we know today, our solar system planets are not really representative. And that also raises a lot of questions. You know, how do these exoplanets form? How do they evolve? what's their structure like, what are they made of, and also, of course, in the broader context of life and habitability on other planets, which is not something I'll be discussing too much today, but is, of course, one of the big overarching questions. And so you can wonder, how on Earth do we detect these exoplanets? Well, this is again the same figure, but now I've color-coded each dot, so each exoplanet, with the detection method that we used. So you can see the majority of the planets have been discovered with transits or radial velocities. And in fact, both these techniques account for 95% of discovered exoplanets. So by far, the majority of the planets are discovered with those two techniques. And what's interesting is that they're indirect measurement techniques. So you might intuitively think, if you want to discover an exoplanet, you just look at the sky and you try to figure out where's an exoplanet. It's quite hard, because these exoplanets, they're not as bright. So and there's also a huge star next to them, which makes it a very big contrast difference. And so we typically use indirect measurement techniques, which uses the star to infer the presence of an exoplanet. And so I'll focus a bit more on this transit method, because it's quite useful to know or to understand this for the rest of my presentation. And I'll show you a figure here for an animation. What's happening here is you're observing a star, and you're taking a light curve. So you're observing the brightness of the system. And if a planet passes in front of the star, you experience a dip in the light curve. And this is what we call a transit. And sort of this transit is directly related to the size of the planet. Again, this is quite intuitive. If you have a larger planet transiting your star, you get a bigger transit depth. And so that means that for 75% of exoplanets, transiting exoplanets, we can already have a quite good estimate of the radius. That's great. We can also do a follow-up observation with this radial velocity technique, which I will not discuss in detail, but that essentially gives you the mass. Then you have a mass, you have a radius, you can also estimate the temperature, and then you have a number of basic properties which you can use for classification, to classify these exoplanets into little boxes. Something that astronomers really like to do, put labels on things. So this is again the same figure, where now I sort of broadly highlighted some parts or some groups of exoplanets. On the upper left corner, you see the hot Jupiters. These are planets that are very large and orbit very closely to their sun, similar to 51 Pegasi b. Then you have a large sort of extended blob here, which is the sub-Neptunes and the super-Earths. So these are planets that are larger than Earth. We are discovering a lot of them, but orbiting, again, quite close to their host star. You have the group of cold gas giants, similar to Jupiter in our own solar system. And then you have this sort of gap, which you might have already noticed. This is a direct consequence of the types of techniques that we're using. We are mostly discovering planets that are close to the star and very massive. That is just because those planets we see very easily with this transit method and this radial velocity technique. So it doesn't necessarily mean that there are no planets at all there. It just means that with the current techniques that we're using, we're not really sensitive to those. Classification is great. That can already tell you a lot of things about these planets. But what we really want to do is go further than classification. We want to go into characterization of these exoplanets. And what does that mean? That means talking about their interior properties, their compositions, if they have clouds or not, potential interior atmosphere interactions, potential star-planet interactions. And this goes way beyond these initial basic properties. And for that, we can look at atmospheres. The atmospheres of these planets are really the gateway into the planet. And so again, I'm showing you the same figure, but now I've color-coded the planets for which we have discovered an atmosphere on. And this probably will not surprise you that this is again these close-orbiting gaseous exoplanets. We are much more sensitive to them, and it's also much easier to detect an atmosphere around these types of planets. So for the remainder of my presentation, I will mostly focus on these close-orbiting gaseous exoplanets. It's already quite challenging to detect an exoplanet, you can imagine that it's even more challenging to detect this thin layer around the exoplanets, the atmosphere. Well, we all know that light, starlight, but also every light, is composed of different wavelengths. And so if you look at the entire electromagnetic spectrum, we already see a very small part of it, so for approximately 400 to 700 nanometers. But there's a lot of different wavelengths that exist. And if we take a transit, so we measure a light curve of a star, and we do that in these different wavelengths, we actually see that the transit depth, so the depth of this dip, is changing with wavelength. And that's peculiar because that means that the size of your planet is different for different wavelengths. So the planet appears bigger or smaller depending on the color you observe it in. Now, this is a sort of a nice schematic that shows the same thing. So on the left, you have, depending on the wavelength, so this is micrometers. Depending on the wavelength, your transit depth varies. You can make that into a figure where you plot the transit depth in function of the wavelength. And that is what we call a transit spectrum or a transmission spectrum. Now, that is theoretically, in reality, it looks a bit like this. So there's scatter or error margin on the observations. But what you see is, you can see very clearly that there's these structures, these broad features in the transit spectrum. And exactly the presence of these features is the presence of an atmosphere. That gives us an idea about if there's an atmosphere or not. And even more, you can sort of use that information to detect different molecules, different chemical species in the atmosphere. How does that work? Well, this is sort of a measure on how different molecules interact with light. And you can see, for example, here, this blob is CO2. What that tells you is that from theory, we know that CO2 is a molecule that likes to absorb light between 4 and 4.5 micron, right? This is exactly matching this big old feature we see in the transit spectrum. What that means is that if you observe the planet in these wavelengths, the planet appears slightly bigger because there's CO2 in the atmosphere that is blocking additional starlight and making sure that the transit depth is bigger. And so that's really great information because that means we have some technique to detect an atmosphere, but also detect different molecules in that atmosphere. But of course, it's all a bit more complicated than this. And there's a lot going on in these atmospheres, a lot of things that affect your observations, your transit spectrum. And I've tried to sort of note down a few of these building blocks, which all matter in some sense to the observations or to the atmospheres. A very important one is temperature. Temperature does not only affect the chemistry, for example, but the direct effect of temperature on your observations is the fact that you have thermal expansion. So a warmer atmosphere is more bloated, more puffy, and so it's more extended, and that's great for the transit observations that we're doing. Another building block is chemistry. All the different components in your atmosphere, they interact with each other, and they make up what is essentially the composition, the chemical composition. And it's the chemical composition that determines which of these features you can see in this transit spectrum. Similar to Earth, similar to Jupiter, we have clouds as well on exoplanets. We have climate, so what that means is that you have large-scale wind circulations that are also affecting your transit spectrum, and you have a whole bunch of other effects, which I will not go over, but these are sort of the main ones. And so they all play a role in shaping your observations, and what makes it more complicated is that they all affect each other. So there's this interdependency of all these different building blocks. The temperature determines on what kind of circulation pattern you get. These both affect the chemical composition that you get. The temperature directly affects the clouds, etc., etc. And then for my thesis, I mainly focused on this chemical composition because that is essentially what it gives you the spectral fingerprint in your observations. And so that brings me to sort of the main goal of my thesis, which is to better understand the chemical composition of closed orbiting gaseous exoplanet atmospheres. How do we do this? We do not use pen and paper for this. We do something which is called numerical modeling, which is essentially we make computer simulations of these atmospheres. So we understand, or we try to understand these different building blocks, and then we pour them into a computer, or at least the physics that we understand, and we try to sort of simulate the environment of the atmosphere. And this can have different goals. So you can do a theoretical study and study the impact, for example, on the temperature, on your chemical composition. You can also make synthetic observations. So you can make a model of your observations. Or you can really just try to exactly recreate or fit these observations. And if there's one thing that you need to keep in mind when we are talking about modeling, is that you don't have infinite resources, right? A computer can only do so many calculations a minute. And so often you're making approximations and assumptions when you're making these computer simulations, simply because you cannot simulate Jupiter over 90 million years, where all the things are in 3D, and that's way too complex for computers. So you're making these assumptions. Often you're making an assumption that you're modeling your planet in 1 dimension instead of 3 dimensions. What does that mean is that you're often neglecting latitude and longitude, and you're only considering the vertical atmospheric column. So that means from just vertical in the perpendicular to the surface, so vertical in the vertical direction. So in the case that you are trying to sort of fit these models to observations, you're hoping that it sort of looks like this, where the red curve is the model, and then you have the data really nicely aligning. More often than not, it looks a little bit like this, where it's just a complete mismatch and you need to figure out what is going wrong. And that is also the secondary goal of my thesis, to bridge this gap that we still often have between numerical models and observations. That's sort of the big conclusion, or the big introductory part. And then now I also want to go a little bit into detail on the specific parts that I did, which is sort of slightly more than half of my thesis revolves around atmospheric characterization of WASP-107b. WASP-107b is quite an interesting exoplanet for 2 reasons. It has a very extended atmosphere. So you can already see that it has a radius very close to that of Jupiter, but only 10% of its mass. So it's a very puffy, extended, bloated atmosphere, which is great if you want to do atmospheric characterization for it. A second interesting part about this planet, it is relatively cool. Now, 750 Kelvin, so around 500 degrees Celsius, that's still warm, or still very warm. But typically when you're studying hot Jupiters, you're dealing with 1,000 plus Kelvin. So that's really still way warmer. So this is interesting because with the temperature of this planet, you can actually probe a different chemical regime, because we're dealing with slightly lower temperatures. Okay. And so there's a lot of questions revolving this planet. It's often depicted as this puffy purple thing. For example, what's the chemical composition specifically at this temperature? What's the cloud composition specifically at this temperature? Why is it so inflated? It has a very tiny mass for a huge radial extent. Why is that? And then what can all of that tell us about core structure, the formation of this planet, etc.? In 2018, there were observations of this planet by the Hubble Space Telescope. And these are the spectra that they took. So again, this is just a transit depth in function of wavelength, a transit spectrum. And what they observed here were a very clear feature of water vapor, H2O. That is not surprising at all, because over 80% of close orbiting gas giants that we have observed, we detect water vapor. What was interesting is that these features, these large expected wobbles due to H2O, were quite muted. What does that mean? Well, here is a model of this planet where you can very clearly see these large variation in the features, but you only observe this tiny muted feature. And that's because there are high altitude clouds in your atmosphere. What does that do is that basically blocks an entire layer below, because you can't see it through clouds in that wavelength range. And so the features that you do see are owing to this very tiny layer on top of your atmosphere that is above the cloud deck. And something that you might not have noticed is that there's no methane features. This seems a bit at random, but why is this not completely at random? If you analyze the carbon chemistry at this temperature of WASP 107b, you would expect a lot of methane. If you look at all the different ways your carbon, or you look at a very, let's say, famous carbon scheme, you essentially know that carbon can be in CO or CH4. The dominant carbon molecule is either carbon monoxide or methane. And if you then sort of compute what this balance between methane and CO should be for a temperature of WASP 107b, you would fully expect a methane-dominated regime. Now, this is a figure which shows temperature, just temperature, and then the horizontal axis, metallicity. Metallicity is a way we use to characterize the number of metals in an atmosphere. Metals are, for astronomers, everything is heavier than hydrogen and helium. So sulfur, carbon, oxygen, that's all metals. And so, yeah, you would expect a lot of methane, and we don't see it. That's a problem. All right, and then I think 2.5 years ago, the same planet was observed with the James Webb Space Telescope, with the MIRI instrument, and all that tells you is that you're observing the same planet in a different wavelength regime. So this is the tiny bit of Hubble Space Telescope data. It's a very busy plot, again showing you a simple transit spectrum, well, twice actually. But what's the interesting part, I think, for you to analyze is this bottom part, where you can very clearly see this double feature, which is from SO2, sulfur dioxide. And then, yeah, of course, we also detect water vapor, because you also detect it in a different wavelength range. And again, you do not see methane. So again, you don't detect CH4. And I want to go in a little bit, want to zoom in a little bit on this detection of SO2 and the absence of methane. When we make these numerical models of WASP 107b, we sort of get this output. So this is a 1D model where you can have just a vertical atmospheric column, where in high pressure environments you're dealing in the high altitude, the low pressure environments are the high altitudes, large pressures are the deep interior of the planet. We have a certain temperature profile, and then we try to model how much SO2 is in the planet. You will see variations of this, so sometimes it's molar fraction, volume mixing ratio, abundance concentrations. These are all measures for how many of that particular species are in there. And what happens if we use these models to sort of play around with a number of parameters, for example, the metallicity, we can see that if you increase the metallicity, you slowly increase the amount of SO2 that is in your atmosphere. This makes quite a lot of sense because you increase the amount of sulfur, you increase the amount of oxygen, so it makes sense that you get more SO2. But this is just to illustrate that we can sort of have a lot of control with these models and change different parameters and see what the effect is then on your abundance. You can also use these models to create fake observations. And if you remember from this figure I showed you earlier, in particular, this double feature of SO2 is quite crucial. That's what we want to recreate. Well, if you make observations of these models, you can see that indeed, if you slowly increase the metallicity, you start to see this very characteristic double feature. And so that's a way we can use these models to deduce the fact that you would have a metal enrichment in the atmosphere of WASP 107b. Another thing we are interested in is what are the chemical pathways that lead to SO2? So what are the different chains of reactions that can give you sulfur dioxide? And for that, we do something called a chemical network analysis. In our models, the chemistry is typically represented as this huge network, this graph of different elements, different molecules that are connected via reactions. And so the different reactions can be fast or slow, depending on the temperature and pressure regime that they're in. And we can use that, for example, to find the fastest pathway between H2S and SO2. And so the fastest pathway means exactly this, to find a pathway which connects all the different steps in between in the shortest amount of time. I specifically start from H2S here. Why is that? Because we know from sort of equilibrium models, so very simple calculations that take into account a normal situation under high pressure and temperature, that most of the sulfur will be in H2S. And so if you make SO2, you have to get the sulfur from somewhere from H2S. If we do this chemical network analysis, sort of there's one pathway that really stands out, and that's when you sort of strip down the hydrogen from your H2S into atomic sulfur, and you subsequently oxidize it to SO and SO2. And in order to enable this entire chain, so this conversion from H2S to SO2, you need hydrogen and hydroxide. And hydrogen and hydroxide, in this case, are from photochemistry. So you have light interacting with molecules in the upper layers, in this case, H2O, and that gives you the necessary sort of radicals to enable this conversion pathway. In reality, it's a bit more nuanced, so you have variations of this pathway with metallicity and different parameters. You also not only need photochemistry of H2O, but what is an overarching theme is that you need starlight. You need a photochemical initiation that liberates these radicals. Okay. So that's it for SO2. The other molecule that we're interested in is the absence of methane. And for that, I sort of want to guide you through a typical chemical structure of this molecule. So again, its pressure in function of volume mixing ratio, the amount of methane in your atmosphere. And if you compute these models, you see that there are three different regimes, and these are very clear for methane. You have the deep interior, where there's high temperature, high pressure, where you have chemical equilibrium. So fast chemical timescales in this circumstance. Then you have a regime where you can actually get vertical mixing that starts to dominate the thermochemistry. And so this effect of vertical mixing is much stronger than the effect of fast chemistry. And so this is characterized by these vertical lines, which you can already see in this plot, and we'll come back in many other plots. What's a crucial point is the quench pressure. Why is that? Because this point sets where this vertical line is. The quench point can be slightly deeper, and then there's a vertical line. Well, there's less methane, essentially. And then there's a third regime, which is the photochemistry regime, where, of course, this is at the top of your atmosphere, where most of the high energy radiation of your star is absorbed. And you can directly dissociate or photolyze methane, and you can also have additional radical chemistry from other photochemical products there. And so using this information, we can sort of, again, play around with our models and try to figure out what is the reason that there's not enough methane in our atmosphere to detect it or to properly detect it. First, very obvious thing you can do is play around with the amount of elemental carbon there is. You can imagine if you just remove all the carbon atoms and there's no carbon to form methane. We use this parameter carbon to oxygen ratio to sort of control this. And you can see decreasing the carbon to oxygen ratio shifts this vertical line left. And so that means that there's less methane. Another effect you can have is that you have very efficient vertical mixing. What does that mean? Is that you can quench your atmosphere quite deep. And so this is sort of parameterized with this parameter KZZ. All that means is that you have stronger and stronger vertical mixing that shifts your quench point deeper, and so you get less methane in your atmosphere. And then sort of the third effect that you can have is that if you have a very warm interior of your planet, you can already shift the balance between methane and carbon monoxide more towards CO. If you remember from the plot I showed earlier, at higher temperature, more of the carbon likes to be in CO because that's much more stable at these temperatures. And so that's also a possibility, the fact that you have this huge intrinsic temperature. And then there's a bunch of effects that are not related to gas phase chemistry, which could also happen. For example, you have a cloud deck, which we already know from the Hubble data, which can also play a role in this non-detection of methane. Then a few months after we wrapped up this study, there was another paper by Lewis Wellbanks et al. And what they did is they took, again, observations of this planet with the James Webb Space Telescope, but now again in a different wavelength range with a different instrument. You can see that you're now dealing with 2.5 to 5 micron. And they found a small little bump that they could relate to methane. So they found actual methane at 3.4 micron, and they analyzed the complete data set, and they found that you have a combination of different effects. So there is some carbon depletion, there is moderate to strong mixing, but by far the dominant effect is that you have this high internal temperature, which explains why you lack the methane that you observe, or at least you observe it in this very tiny feature, because if there were more methane, this feature would really dominate. And so that has quite some implications for our picture of this planet. Before we had this nice James Webb data, we are dealing with a planet that is quite low in mass, but very puffy. And so you have to figure out the interior structure based on those parameters. And if you're assuming that the core of the interior is not very hot, you have to assume that there's not a lot of mass in there. So there's only 5 times, you can't see the little Earth symbol. Yeah, okay, 5 times the mass of the Earth. And then you would need a huge, puffy, purely hydrogen and helium envelope to fit the radius. And that's really a challenge from planet formation scenario, because that would mean you have this very tiny core that somehow accretes a huge amount of gas. Not only that, but also the gas is not metal enriched at all. It's almost purely hydrogen and helium. But now when we have this evidence of a hot core, we can actually relax these assumptions a little bit, and you can allow for a much larger core, so around 22 times the mass of the Earth, and also an envelope that is enriched with metals, which is again in agreement with, for example, the SO2 detection that we have. And that's great. We could, in theory, stop there, but we didn't. About a year ago, we wondered, like, we have all this nice data, and we can make a lot of conclusions, but are we sure about those things? Are we sure about the things we infer from the observations that we have? And that's sort of the inspiration for the last part, which I want to talk about, which is how reliable are the retrievals that we use. And so typically, you retrieve these atmospheric properties, such as the intrinsic temperature, etc., by using a sort of a cycle between models and comparing that with the observations. So you make a model, you check if that matches up with your observations. If that's not the case, you sort of make a new updated model, which is hopefully a little bit closer to the things you observe. If you want to do that in a statistically robust way, in a statistical framework, you need to do this 10,000s, 100,000s of times, which is not easy to do if all of your models are very heavy to compute, and they take a lot of, for example, a couple of days to make. So when you're sort of making the balance in which models to choose, you often choose for parameterized models with a lot of assumptions, but that are very easy to compute in high amounts. And you typically don't look at these more physically accurate models, for example, where you really include all the disequilibrium chemistry effects that we were talking about earlier. What we did is we tried to make this hybrid setup where we combine sort of the best of both worlds. So every time we need to compute a new model in this iterative cycle, we actually use data which we already computed and we stored in a database. So this is a pre-computed grid of close to 1,000 models. And during the iteration, we just very quickly interpolate from this existing database, and we do the final step on the fly or in real time. And so this drastically reduces the computation time and still allows us to use it in this sort of retrieval framework. So yeah, and we use that to answer a couple of questions. So are we sure about the atmospheric characterization of WASP 107b, specifically these 4 parameters? So that's metallicity, carbon to oxygen ratio, intrinsic temperature, and then parameter related to the vertical mixing. And then we really wanted to explore how our different approximations and assumptions impact our results. Now, I won't go over all the, actually I have more time than I still won't go over all these results that we obtained there. They're in the thesis, obviously, and they were also published last week. Just plugging it there. But I do want to highlight one specific thing, and that is the fact that we find that this intrinsic temperature is quite hard to constrain, which is something that we used earlier to make our picture of the interior of this planet. And so why is that? Sort of from a top-level perspective, it's because you're fitting this feature, you're inferring the value of this feature based on this single methane peak. And so any other effect in your model that affects this wavelength range and affects the feature of methane that you have will also have an impact on the value you retrieve for the intrinsic temperature. And you need to be very careful, and you need to really understand what you're doing, because it's very easy to make assumptions that impact this region, and so sort of bias or affect your intrinsic temperature. A specific example is the fact that you have this high altitude cloud deck. And if we compare the sort of the retrieved location of this cloud deck with our models of WASP 107b, you find that they're around at the same pressure as where your abundance of methane starts to decrease due to photochemistry. What it effectively means is that you're shielding the bulk methane present in your atmosphere with your cloud deck. And so it doesn't really matter which intrinsic temperature you assume in your models, because you can't see it anyway. There's clouds that are covering it up. And so that sort of depends, or let's say the exact value you retrieve depends on how you treat your clouds in your models. You can parameterize these in different ways, and they all have an effect on this interior temperature. So what are the consequences for our current view? Well, instead of arguing that our current view is wrong and then it's impossible to have a high intrinsic temperature, we're just arguing that we need to make sure that when we have this nice data of James Webb and we're throwing very complicated models, that we also really understand how these models work and how they affect the things that we retrieve. So there's other evidence for this bloated core and this high intrinsic temperature, namely the fact that you still have a huge extended atmosphere. But simply from this feature, you need to watch out if you're using these hybrid retrieval methods. That already brings me to my conclusions. The first goal was to better understand the chemical composition. And I think I gave you an idea, specifically based on WASP 107b, how we can sort of analyze the chemical pathways that interconnect all these species that we have in our atmosphere. There's quite a interesting amount of, or a large amount of interesting dependencies on different properties in our models. And in general, you have to remember that this atmospheric chemistry is really a complex interplay between these different building blocks that we talked about. Secondary goal was to bridge this gap between the models and the data that we have. I think you can remember that the numerical models we have are great, but they're never perfect. And so it's important that you realize why they're not perfect and what are their limitations. And then these advanced retrieval techniques that we talked about, these hybrid retrieval techniques, I think they're really necessary in the current era of James Webb, because this gives us a lot of beautiful data, but we have to really be careful in how we use them. And with that, I would like to thank you.
Thank you very much, Thomas. Before opening the discussion, let me introduce the members of the examination committee. So, Professor Andrea Chiavassa from the Observatoire de la Côte d'Azur. He's online here. We can see you. You can hear us, I guess.
Yeah, everything. Hello, everybody. Everything's fine.
All right. Well, not so well. Then further from me, we have Professor Jeroen Bouwman from the Max Planck Institute for Astronomy. Then Dr. Robin Bayens from the University of Amsterdam, the Netherlands. Professor Jeremy Harvey from the Department of Chemistry of the KU Leuven. Professor Denis de Frère from the Department of Physics and Astronomy, Institute of Astronomy. And Professor Leen de Sen also from the same department, from the same Institute of Astronomy, and she's the supervisor of Thomas. Myself, I'm Professor Enrico Carlon from the Soft Matter and Biophysics unit of the Department of Physics and Astronomy of this university. Okay, now we have introduced everyone, and now it's time to opening the discussion, and I hope that we can start from Professor Chiavassa. If you can hear us, we could see you, but not hear you so well.
Hello, does it work? Hello, can you hear me? No.
Let's see.
Hello? Hello, does it work? Hello? 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 Can you hear me? I don't hear anybody anymore. Hello? Thomas?
Hello.
Can you hear me?
Can you hear us now?
Can you hear us?
Yeah, I hear you perfectly, but can you or not? Yes.
Okay. So you can start your question.
So can I talk?
Yes.
Yes.
Okay.
Please.
So I'm sorry. First thing, I just want to congratulate. I found very pedagogical, very interesting the way you presented today and the way you presented your PhD manuscript. I really enjoyed to read it, and we will share also with my student. So thanks for that. I'm sorry not to be there, but I have commitments here in Nice that led me to move in this moment. I have a couple of questions just on general thing. One concerns your work you didn't present here about end dwarf activity, which is I think is your first paper.
Yep.
Could you really, in a few words, because I think that is also related somehow. Also, I mean, it's definitely related for the future of the JWST and many others observation we're going to do about atmospheric study for these kind of planets. Can you just comment on that and say what are the forthcoming for your work?
Sorry, what was that last part?
What do you expect that your work will bring actually to the community for actually trying to characterize better the stars behind the planets?
Yeah. So there was another part of my thesis which I didn't really get a chance to talk about. Well, I had some minutes left, so maybe I should have. But which is the effect of stellar activity on your exoplanet. So stars, especially the lower mass stars, so similar to our sun and even lower in mass, they have different phenomena related to what we call stellar activity. And so one of these phenomena are stellar flares. And this is sort of what you can see. These are rapid outbursts of high energy radiation from the star that is, of course, or can impact your planet. And so we try to analyze this a little bit. I won't go over all the results. Nope. We try to analyze, again, model these planets that are impacted by these stellar flares and see what the effect would be. And so these are, again, transit spectra where we subtracted the spectra before we had any flaring. And then we computed a bunch of transit spectra during the flare event. And the goal of that was really to see how your observations of a planet would be impacted if there's flaring on this atmosphere. And so I think the question is what are sort of the main takeaways from this study, and what is that what is the central message behind this study? And I think the most relevant part is that we found that you can have 200 to 400 parts per million difference in the spectra compared to when you do not consider flaring. What does that mean is that you take observations, they can have, it's not super significant, but it's a couple of hundreds part per million difference in the features that you observe compared to when you do not include this flaring. And so additionally, these features, they sort of fluctuate between 100 and 300 parts per million. What does that mean is if you observe it with the James Webb, for example, one time you could observe this feature at minus 200 ppm, and at the other time it could be plus 100. So there's this noise that is introduced by stellar flaring. And I think this was one of the first things I did in my PhD. After this, we observed real planets, and we figured out that there's a lot more we don't understand. And so a lot more that has an effect far larger than this couple hundreds part per million. But so I think that this is sort of the main message, is that if you do not include this, you're probably you're sort of miscalculating your observations, or you're interpreting them wrong, because there's a couple of hundreds parts per million introduced by these stellar flares. I think that's a very long explanation that hopefully makes it clear.
I think it's important also to mention this part. Yeah, sure. Thanks a lot for that. Then, if I can, I still have really a couple of questions, to be quick. But one thing concerning the clouds, which I think is kind of, your data-driven work is very interesting here. So, what you would suggest then to, so you described very well the limitation actually of the analysis of the model dependencies, etc. So it depends on many things. What would be the best way to proceed to better characterize these clouds in the future from a numerical point of view and physical point of view? What do we need to work on for describe really well these clouds in these temperate planets?
So all the different cloud setups that we used were used in post-processing. I think the slide that should, yeah. So this is sort of the setup. If I use my mouse, can you see it? Yeah. So this is sort of the setup that we use, and it's only in this step when we translate our chemical models to a spectrum that we introduce these clouds. And so we use a parameterized form. What you could also do, theoretically, is really compute the cloud structure from first principles, so from your temperature profile, from your chemical composition. There's a reason we did not do this, is because it's really poorly known. So it's very, we don't know exactly how clouds form, especially in these gaseous exoplanets, because the way these form are quite different from what we know on Earth. So the way forward, I would say really invest or do more research on how these clouds form and which types of clouds you expect at which altitudes, at which temperatures, and so make this type of work feasible to integrate it in a retrieval workflow. Because I think there's been colleagues at the Institute that did research on this, and I think they managed to do it in 0D, which means a single temperature pressure point, and to compute a sort of a mixture of clouds. But to do this in a fully integrated retrieval setting, yeah, that's not possible right now.
Thank you. I would have, if I can, one last question concerning what you cited, what you analyzed so far are JWST data. So kind of, let's say, medium-low resolution, spectral resolution. What would you get if you can observe the same planet or a similar planet from the ground using high spectral resolving power? I don't know, even if you think about the future with ELT, with like the MATIS, since you were showing this kind of range, wavelength range, or ANDIS, for instance.
Yeah, that's a great question. I think one thing you'll really or likely be able to constrain is atmospheric motion, because if you're really at high resolution, you can probably figure out Doppler shifts that are owing to atmospheric circulation. So that would really help us to understand sort of the three-dimensional nature of these planets and not just treat them in 1D. That's one obvious thing I would say is useful for at least for these types of planets, so the close orbiting gas giants.
Okay, I think I'm fine. So I thank you again. I know I have other questions, but I don't know how much time. I don't know exactly how it works. So I can come back later if there is time left. Thanks a lot.
That's great. Thank you, Andrea.
Okay. Thank you. Thank you very much. So I give.
So, dear Thomas, I'm very happy to be here today. You did a fantastic job, so I'm very happy to see to have this now. I see now I have the final thesis in print form now, just in my hand. So yeah, you did really, really well. And so as a first question here, sort of the audience here, I had to think about my own PhD, which is defense, which is some years ago. And the first question, and probably the most important question asked to me, and I'm going to ask it the same question to you today. So, did you have fun?
What was your answer to that question?
I had super much fun doing my PhD.
For the sake of the defense, yes. In a more honest way, I think the fun part was the fact that it had quite some ups and downs, and it's quite nice to be standing here and to be able to say that at least I'm almost there. Don't want to jinx it. So yes, and at least the science part was really fun. You're doing state-of-the-art stuff, so yeah.
Good to know. So now more for the more serious questions. And so I mean, you did a fantastic job with also with the different, very different topics. But one of the things you were focusing on is also to discuss a bit more on how to do this modeling to not just 1D models, but going to higher dimensional models, 2 and 3D models, and how to actually use this for retrieval. So I would like to ask you a more general question. I mean, I guess for some systems, you might 1D models might not be a too bad approximation. But for others, I guess that basically 1D approximation completely breaks down, or you get really wrong results. And so I would like to know from you under what conditions or what type of systems basically you really have to go to higher dimensional models, and 1D approximation, which is the typical thing to do for retrieval modeling, is really a wrong approximation.
Yeah, I think the temperature is really a central quantity there. There's been studies that show that if you stick below equilibrium temperatures of 900, 1000, that you're typically well in a 1D setting. Why is that so important? Because, well, yeah, this might be an interesting slide. Why is that so important? Because otherwise you get this asymmetry between the different sides of the planet that you're observing. And so if you go into way warmer planets, there's a large asymmetry in the limbs that you observe. And yeah, this is should have made this schematic a little bit bigger. So this part and this part are the different limbs. Typically for a planet like WASP-107b, a good assumption is 1D. That is until there were NIRSPEC observations which actually detected a slight limb asymmetry in this planet. But it's still only 150 to 200 Kelvin. So it's quite limited. If you go to warmer planets, really hot Jupiters, there's been plenty of research that shows that these limb asymmetries, they can quite drastically affect the way you observe your planet. Specifically, you can have one side that is much more warm and sort of more extended and has different molecules because you're dealing at a different temperature than the other side, which is perhaps more cloudy and is a bit more cold. So I would say typically sub 1000, you're fine with 1D models, but apparently, James Webb is really good and can really differentiate between 100 to 200 Kelvin differences in the limbs. So,
Yeah, thank you. That was for this clarification. And so one of your chapters, you go into retrieval analysis, or basically how to use, say, more forward modeling or more computational intensive models. Do you also see the same framework you now developed to do retrieval on these type of models with an interpolation between the models? Could you also use this to do more of this type of work for what you just showed for different day and night side limb, or to retrieve also more in 3D structure and in chemistry on these planets?
Yes, I would say so. I mean, currently I'm using 1D models in this hybrid retrieval, but you could opt for this 2D model that I also used. The problem is always, if you introduce more complexity and more degrees of freedom, it's harder to retrieve anything. I think there are probably cases where you can opt for this 2D model within a retrieval setting. One of the big downsides in our models is we have these different cloud parameterizations. You can opt for a really simple one, and that reduces the degrees of freedom to one additional parameter, or you can really have a complicated crowd prescription with I think 7 additional parameters. If you do opt for this 2-dimensionality in your model, you'd have to make choices on other aspects, such as complexity of the clouds. But if you're interested in specifically figuring out this limb difference, I think there's probably a chance you can integrate this 2D model there. Yeah.
So just a final question before we move on. I would like, there was this, I mean, you did also very extensive work on the SO2 modeling, especially for WASP-107. We have this very good detection. So was this just recent paper by Crossfield et al. I don't know if you've seen this on AstroPH. I think I just saw yes, exactly.
This was not agreed upon by
no,
the way.
and so I'm happy that you still followed basically what was just coming out on this, because that's actually what I want to ask you a question about, because the conclusion in that paper was that the SO2 is basically sensitive to metallicity, overall temperature, and the CO ratio. Not so much on the XUV iteration and the vertical mixing rate.
I would agree.
And completely independent, as what you see there on the internal temperature. So I just read it now from exactly.
So what do I pay you for this question? Or?
You came very well prepared, and so and so I would like to ask you now. I mean, is this now in agreement with the work and the conclusions you did, or are there fundamental differences? Because I mean, also now we have this figure here, so that's nice to show. Because if you see this, I mean, there's several. Het P27, 26 would be agreeing with this, but basically the rest not so much. I mean, there's plenty of non-detections in the area where you would expect them. And I find that highly problematic. So could you comment on this and see what the issues are here?
Yes, yeah. So the reason or the partial reason I included, because it agrees so well with what I've done. So one of the conclusions of this last chapter was that you have quite a nice metric to study the metallicity with SO2, and this independence on the internal temperature. That's, of course, your SO2 is formed quite high up in the atmosphere due to photochemistry, and is not really affected by the deep layers. And so, yeah, there's quite a lot of agreement, I would say. Then the secondary question I would say is why do you have all these different planets that you don't detect SO2 on? And that opens another box of possibilities that could be purely detection effects. That could be, one of the things we researched a little bit is as well the effects of gravity in the different UV radiation fields. I mean, this can all play a role in whether you detect it. And I think it's important to differentiate the detection of this molecule and whether or not it's present. I think that's the entire story of the methane in this planet really shows you this. So, but it's a really interesting paper because it's one of the first ones that really tries to do this on a population level, and not just on individual-based planets. So I think, yeah, this opens up just another box of questions. Yeah.
Thank you.
Yeah. Thank you.
Yeah, sort of. Yep, that's it. Yeah.
Hi, Thomas. First of all, congratulations for your thesis. It was a joy to read. Of course, it was familiar because the papers were also a joy to read already. And I also think you did an excellent job explaining the concepts and all the science questions that you explored in depth. And you did a great job at explaining this in the presentation today. So thank you for that.
Thank you.
We also already had the chance to really discuss the scientific results of your thesis in quite a lot of detail, actually, during the preliminary defense and also afterwards in private. But I still have a couple of questions left. And the first one is actually inspired by something you said in the introduction of the presentation today. And that is, if I remember correctly, that the solar system is not represented in the current exoplanet population. So I think I can agree, but I also have some thoughts about that statement. So can you say something about the presence of our solar system and put it into the context of the exoplanets that we know, or maybe that we don't know?
Yeah, I think there's a subtle difference in me saying are not represented in the distribution of exoplanets or not representative of, I meant to say the second, I'm not sure what I said at the end, because the first one would imply that the solar system is incredibly special and you don't see any planet that we see in the solar system in the distribution of exoplanets, which is not the case. So a number of differences with the distribution of exoplanets that we know today is, for example, the most common exoplanet that we think is there is the so-called super Earths. So they're around twice the size of Earth, which is obviously something we don't have in the solar system. So in that sense, if the most common exoplanet, and I think it believed that 40 to 50% of all stars that host planets host a super Earth, in our solar system, there's not that. On another, let's say, demographics note, you also have the multiplicity of these systems, so the amount of exoplanets that orbit a star at a time. The solar system has 8, 9, depending on which year you say this. And there's only one system for which we've discovered 8 other planets. I think it's Kepler-90. And so it doesn't mean that there's no other systems with 7, 8, 9 planets, but that means that at least what we know now, there's quite some differences in what we know between the two systems, or the distribution of exoplanets and the solar system. So in that sense, I guess there's some difference, but I wouldn't say that they're not represented. I mean, we do see cold gas giants in the distribution of exoplanets. So yeah.
And do you see that changing in the future?
Well, yeah, I hope so. If we're ever going towards like twins of Earth, like actual a little bit more far orbiting rocky worlds. So I guess, yeah, this will change with like the ELT also, that will sort of be able to probe this range a little bit more, or this area of the plot I showed. Yeah.
Thank you.
Okay.
I have a second question, and you spent a lot of time going really into detail with photochemical modeling, and you even did some chemical pathway analysis to really figure out what species you can expect under which conditions. And I was wondering, do you have a sense of what is currently the biggest issue for photochemical modeling? Is it in the chemistry side of things, or is it more in the way we treat the planetary atmosphere? I would appreciate your thoughts on that.
It's a very nice question. The biggest issue, I would say that there's a number of, not issues, but at least uncertainties. I mean, there's a lot of factors that affect your photochemistry. It's photochemistry, so you need to characterize the star very well. It is very difficult to do that in the high energy range of this the electromagnetic spectrum. That is a big problem. Another big problem is the fact that you need to have data to put in your models. So you need to have information on how how molecules interact with each other, how they interact with light. And these are from experimentalists, from theory. And there's a lot of work to be done there because we're discovering dependencies of this data on temperature, dependencies on whatnot. And I think the biggest problem or the biggest challenge is also the thing that affects the chemistry the most, which is the temperature. And I think to really understand, especially the multidimensionality of photochemically produced species, you would really have to have a good idea of the temperature and also how the temperature changes when you have photochemistry. So I would say, well, in all sort of the effects that I modeled, you can always see that if you play around with the temperature, that has by far the largest effect on whatever you observe in your atmosphere. So I think that's still the biggest issue, is that you have to have a really good idea about the temperature background, I would say. Yeah.
Okay, thank you very much. I think what was also actually quite scary for me to read is that you did a great analysis of this planet, WASP 107b. I think it's one of the best studied planets we have, basically, of all exoplanets, right? And you find a result that is clearly different from what people before you have found. And I think these people even found a result that was different from people before them, all using very comparable methods. So this is quite scary, I think, if we want to understand exoplanet atmospheres. So my question is, what hope do we have for population studies of exoplanets where we want to see a really overarching trends if we cannot even agree on a single case?
Yeah, I agree. In some sense, it's a bit scary to see, or at least very confronting, because we are all using very similar models. At least the way you introduce photochemistry or mixing in your models is all very standardized across different people, and we still get quite different results when we do these retrievals. I think that's a major part why we did this final chapter or this paper, is to really highlight the fact that you need to understand what you're doing before you can use that to infer things on the data. And you already see this popping up, that you sort of have this data information studies and these studies that really try to not discover something new in the planet, but revisit the data and figure out why we see certain things, and if the thing that we see disappears if you make it a different assumption. And I would say the only solution to that is to do more of these studies where you compare different models, where you really go in depth. These are not always the most interesting ones to do, because you spend a lot of time just figuring things out and tweaking buttons, and you're not discovering new things in new data. But they're absolutely necessary once we're going towards things such as the Ariel space mission, which will really go for a population level atmospheric characterization. So yeah, a lot of work to do, and keep doing that.
Yeah. All right, so there's still hope.
Yeah, I would say, yeah.
Okay,
Yeah.
Thank you very much.
Thank you.
Okay, thank you, Thomas, and congratulations. I followed your PhD more or less from the beginning, through the harder times that you mentioned and the easier times, and it's come out pretty good, I have to say, so well done.
Thank you.
It's always nice to see the printed version. You didn't comment, I think, that some of the credit for the printed version is to your mother, who is... So I wondered, does the cover have any scientific link to your thesis, or?
With a sprinkle of artistic freedom, yeah. A lot of sprinkles, yeah.
So these are flares that we're seeing, or
No,
what?
yeah, the idea is that this is a planet. not
It's a
star.
planet.
Yeah. The idea is that you have like this mixture, this whirlpool of different colors, which are the different chemical elements or molecules in your atmosphere. And you have a slightly lit up terminator, which is of course due to the star, which has been cut off because it's on the cover. But that's sort of the idea.
Okay.
Yeah.
Okay. Very nice. So you already had quite a lot of questions, and in fact, some of them have overlapped with ones I was planning to ask. So I'm going to ask one rather general question. So Robin just alluded to the the challenge of uncertainties in this field, and I was wondering to what extent. So exoplanets are annoying because they're a long way away. So you can't put them in the lab and study them the way we'd like to. But we do have a solar system. And I wonder what you can learn about the uncertainties from how well similar techniques work for our own planets, our own solar system. Of course, you can't put the other planets in a lab either, but they're a lot closer. So you've got a greater variety of measurements.
Yeah.
There's no hot Jupiter in our planet, which I think is probably a fortunate thing for us.
Yeah.
I guess, but
yeah, I think the most obvious thing that comes to mind is, is the idea of this simplified but still commonly used two-layer model where you have a core with then a huge envelope. I think the Juno mission revealed that this is definitely not the case for Jupiter. But for exoplanets, at least, there's not really an incentive to make these things more complicated because they're so out of reach still. And so what turns out to be the case for Jupiter is that you, instead of this very clearly defined core, is that you have this fuzzy core that sort of leaks into the atmosphere. So it's not really a very too structured model, but it's more of a dispersive thing, which obviously would change your viewpoint if you're trying to link the things we see in this atmospheric window to what's happening in the core. So I think that's an obvious link between the solar system and what we have for exoplanets, I would say.
Yeah. So you've mentioned things like the uncertainty of the effect of clouds. The clouds in these hot Jupiters are quite heavy elements, silicates and things like that. And I guess the clouds of silicates are not so easy to see in the solar system. But can you say whether clouds of lighter molecules and their impact on spectroscopy, whether that informs you on how big you think the impact is on WASP 107b or other exoplanets?
Yeah, so essentially the type of clouds that you're observing depends very much on the temperature, and so it's very different for these hot Jupiter planets than for Jupiter in our own solar system. I think, of course, there is overlap. I mean, if I remember correctly, sort of the hazy particles in Jupiter's atmosphere, so this soot kind of particles. I think most of the data that we have on their opacities and stuff is from Jupiter. So it has been used in exoplanets to model haze. To what extent that is accurate, I'm not that sure. I haven't dealt with hazy particles myself, but there are overlaps. But yeah, it's like you already mentioned, the big difference is the temperature regime, which changes everything related to clouds. So it's difficult to compare, I would say.
Okay, congratulations again, and thank you.
Hi, Thomas, congratulations on the work. This is really excellent work and very important work in exoplanet science. And also the presentation today was really didactic. I really enjoyed it and was great. Since you're on that slide, I had a small question on that slide regarding the core. Can you comment on the composition, what we know about the composition of the core, and how do we how can we separate the core from the atmosphere? How do we do that?
Well, you don't see the core, that's the first thing. So you see the atmospheric layers. I think typically you assume a mixture of silicates, iron silicate core, I think is the standard for these models. There's probably a good reason you assume that, to ask a geologist or something. The relation to the atmosphere is always tricky because we don't really know, like the example of the fuzzy core with Jupiter, we don't know how these two interact. And so the entire story about intrinsic temperature, that's one way of connecting this to the interior. But otherwise, in terms of composition, it's quite hard to link sort of this narrow atmospheric window that we observe to the bulk properties, let alone the properties of the interior of the planet. A lot of times people assume that it's the same. So you have this sort of general metallicity or elemental composition. There's probably ways in planet formation people where you can assess, sort of due to pebble accretion, how many metals are deposited into the atmosphere. I don't think those models are that on point that you can sort of take that as a ground truth to start from. So yeah, that's a very big challenge. It's to make that connection between the two regimes. Absolutely.
Do we expect the core to be similar composition as planets that we have in the solar system, like Jupiter or Saturn?
I do not know the composition of the Jupiter's core, so I also don't want to start guessing at this point.
No problem.
No.
So you mentioned one of the objectives of your thesis was to bridge the gap between models and observations, and this is a challenge that we also face in direct imaging. In your thesis, what was the most difficult and the most surprising gap that you faced?
I think the most difficult part was the clouds, because I started out completely neglecting them in my first chapter, and then slowly throughout the thesis, it became very obvious that this is sort of the next big thing that we need to worry about. So to figure out what is still a correct way to include them in your models without needing to fully compute them from first principles was quite a challenge. So it is difficult and challenging, I guess.
Surprising.
Surprising, yeah. I would say because the impact of these different conclusions on the interior temperature are quite significant, and they quite have some impact on the existing literature, because sort of everybody agreed on the fact that, okay, we solved the planet. It's a hot core. There's no methane. This all makes sense. And so that's why the planet looks like it looks on the right instead of on the left. To then maybe pour a little bit fire back on the discussion and to really ignite it back, because we're not sure about this scenario, is I think the most satisfying part of my thesis, which is I think will have an impact, I hope. And I hope some studies pick this up and try to really further explore how we can still match this results with the overarching picture of the planet.
Okay, and I have a final question. Can you go to your slide 61, I believe? Yes, so you mentioned that here one challenge is that we only have this one CH4 detection, but it's also a very narrow observing window. So would we expect to detect methane at, let's say, longer wavelengths? How, and would this help in understanding the internal temperature of this planet?
Well, it's a narrow window, but this is just a zoom in of the entire available spectrum, which is, I think, from 1.1 to 12.2 micron. Yeah, if you go beyond 12.2 micron, it's like, I guess, the MRS mode of MIRI, I think the data quality might not be sufficient to really narrow it down if methane is really in low abundance there. Also because you're running into contrast issue with the star, I guess. So I'm not sure about the data quality there. Maybe.
I was not thinking beyond 12 micron, but let's say there are methane lines around 8 microns, for instance. And
Yeah, maybe I have a plot.
Yeah.
Just not sure if I do actually. Just going. Yeah. Yeah. Here.
yes, so here we I guess we don't see the methane lines, but we can expect methane lines at this wavelength at micron.
Exactly.
And here it's not the case. So can this be used to constrain the internal temperature of the planet, or?
Well, the initial sort of models we ran for this planet tried to include methane to explain this peak that is now SO2, or at least now we know that's SO2. The problem in this wavelength range is that you have this very broad feature, which is parameterized here, but just owing to the clouds, specifically these silicate clouds in this planet. And so I think here you're definitely shielding the methane with your clouds. So in these wavelength range, I think you just detect SO2 and H2O from the gas phase chemistry at least. Yeah, this is really a significant feature though. So you can really, it's quite a robust detection at least.
Okay, thank you.
Thank you.
That's all for me.
Thomas, congratulations already. I promised to maybe ask you one question. You maybe know already the question, but it's slightly different. How do you define north on a planet?
You sure delivered on your promise. So how do we define north?
North for a planet, not east, north.
So we can't really use magnetic fields because we don't really have an idea about the magnetic fields there. I mean, so first of all, you don't, so you stay away from that. Yeah, I mean, it's just a convention, I would say. Yeah, I think it's maybe related to like what you just hinted at, like the right-hand rule, you say it in English, yeah, where you take the rotation of the planet and then where your thumb ends up is the.
That's it. That's
north.
it.
Well, there we are. Yeah.
I need that question for later on.
Oh, okay, okay. Exciting.
Okay, so I have no questions myself. So we are done with the questions from the examination committee, and now it's a custom to ask if the audience has questions. Any kind of questions? Yes?
Hello, Thomas. Very nice presentation. It was wonderful. So you can see all of these nice spectra, and you already know quite a lot of the chemical composition of an exoplanet. So I guess to me, given that I don't have the background here, it is not entirely obvious what additional things that we can learn through these simulations. Can you quickly summarize some things that we can learn that we cannot see in the spectrum?
Yeah, the spectrum is always just one line. And so the entire three-dimensional planet is reduced to one line. So there's a lot of effects in this three-dimensional planet. What we talked about, these different building blocks. So the circulation, for example, all has a tiny effect on the one line you see. But if you can relate these simple lines to what is happening on the planet or the three-dimensional nature of the planet, for example, this wind circulation, you can use this to understand better how much of the starlight is observed, because we know from theory how your climate is shaped by the radiation it receives. You then can say something about the different elements in your planet or the different molecules, because depending on how many of these molecules are in there, more or less radiation is absorbed by the planet. And so I would say that there's a lot of sub-layers of complexity that it's difficult to relate to the spectrum. And there's also, by the way, there's other techniques which you can use for different size questions. So that I mainly talked about is transit spectroscopy. You have different techniques, such as the high-res spectroscopy, which we talked about. But yeah, I would say, does that somehow answer your question?
So you're trying to make sense of the noise through those simulations.
It's a poetic way of, yeah, say yes.
Thank you.
Okay. Thank you. So now it's time for the examination committee to leave this room, and we will soon be back. Ladies and gentlemen, dear colleagues, I will now proclaim the result of the deliberation by the examination committee, appointed for granting the doctoral degree in science, astronomy, and astrophysics. Thomas Konings has presented to the faculty the PhD thesis on the topic Atmospheric Chemistry of Gaseous Exoplanets, Data-Driven Modeling and Statistical Inference, in partial fulfillment of the requirements for the PhD in science, astronomy, and astrophysics. And Thomas Konings has defended this thesis in a public session before the examination committee. The examination committee has determined that all requirements concerning the granting of the doctoral degree that are prescribed by the law and by the university regulations have been met. Therefore, on behalf of the rector of KU Leuven, I confer upon Thomas Konings the degree of Doctor in Science, Astronomy, and Astrophysics. By obtaining the doctoral degree, you commit yourself as a doctor to act also in the future in accordance with the basic principle of research integrity, as described in the ALIA European Code of Conduct, reliability, honesty, respect, and accountability. I close the session.